mute your, yes. Please mute your microphone and leave your camera off when not speaking. And if you have questions and comments during the introduction or during the presentations, please share them with all of us in the chat. The questions will be answered, first of all, in the end of each presentation. We have some minutes, and but also during the Q&A session in the end of the webinar. And the questions will be posted anonymously. I will read the questions. But you are also welcome to raise your hand and ask questions orally if you want to, but the questions written in the chat will be prioritized. And since we will use the chat for questions, please avoid to have a parallel discussion in the open chat, because then it will be much more difficult to distinguish what is questions, etc. So I welcome you all to the final webinar of IEA HPT Annex 52, long-term performance monitoring of ground source heat pump systems for commercial, institutional, and multifamily buildings. My name is Caroline Haglund Stignor. Annex 52 is part of Annex 52 is part of the Technology Collaboration Program on Heat Pumping Technologies, and I work for the Heat Pump Center, which is the communication center and program office of this Technology Collaboration Program. Here is the agenda for the webinar today. We will start with an introduction about HPT TCP, and thereafter the presentations regarding the annex will follow. And in the end, we will have a session for questions and discussion. So now I will give some information about the Technology Collaboration Program on Heat Pumping Technologies within the IEA. So what is the HPT TCP? It is a technology collaboration program that's been ongoing within the umbrella of IEA since 1978. It is an international framework of cooperation and networking for different actors working in the field of heat pumping technologies. It is a forum to exchange knowledge and experience, and it contributes to technology improvements by performing research, development, demonstration, and deployment projects, what we within this context call annexes. It is within these annexes where knowledge and experience are generated and exchanged. The scope for the TCP includes heat pumping technologies used for heating and cooling, air conditioning, and refrigeration. And it covers applications in residential and commercial buildings, industries, thermal grids in cities and communities, and also in other types of applications. The TCP has at present 17 different member countries. You can see the names of the countries here, and they are marked with red on the map. So we have member countries from America, Europe, and Asia. The annexes, the international collaboration projects within the HPT TCP is the core activity, the main activity within the TCP. And we perform such projects within some prioritized areas. The first one is affordable and competitive technologies for heating. The second one, more efficient cooling and air conditioning. Then we have a third area that we call flexible, sustainable, and clean system solutions. A fourth one about digitalization and Internet of Things related to heat pumping technologies. The fifth one about new or special markets and applications for heat pumping technologies. And finally, new alternative for natural refrigerants, lower global warming potential. And I will not go through all the titles of the annexes. You can see the red ones are the finalized ones, the blue ones are the ones which are ongoing, and the gray and black ones are in progress to be developed. And you can see I have marked out Annex 52 here. Another important activity within the HPT TCP is the Heat Pump Center, which works with information and dissemination and communication, which I work for. We publish final and part reports from the projects. We publish a magazine, an electronic magazine free of charge 3 times a year, and we send out a monthly newsletter with news related to the technology. We run a website where you can find information about all the ongoing projects and annexes and news, events, and information related to heat pumping technologies. We're also active on social media, LinkedIn, Twitter, and WeChat, and I just posted the link to our LinkedIn account in the chat, so please follow us there. Heat Pump Center do also work with support to EXCO, which is the board of the HPT TCP, with representatives from all the member countries. We support the national teams, which are the national contact points within the different member countries for the TCP, and we support the project leaders for the annexes, which are often called operating agents. Besides that, we work to stimulate a generation of new activities, especially new annexes. We organize every year national experts meeting to discuss and develop new ideas. And we support IEA publications. We provide with data, expertise, knowledge, and context when important publications are produced. And we do work with other outreach activities, such as attending conferences, fairs, and giving presentations, etc. The TCP organize every 3rd year an international conferences about heat pumping technologies. The next one will take place in Chicago in US in May next year, and it's still possible to submit abstracts to this conference. The deadline is this week on June 15, so if there is still a possibility for you to submit an abstract if you have not done so yet. And I hope to meet many of you there in a year from now. That was my final slide of my presentation, my introduction about the HPT TCP. And now I will leave the floor to Signhild Gelin, who will give an overview of HPT Tcp Annex 52. So stop share.
Thank you very much, Caroline. Now I should see if I can share my screen. There. Yes, so I am the operating, or I was the operating agent of Annex 52. And my name is Signhild Gelin. I work at the Swedish Geoenergy Center in Sweden, and we have been coordinating this 4-year project, which I will now try to give you a brief overview of. I must stress on that what I will now, or what we will present to you within this final webinar, is just a small sample of all the work that has been done by so many people over these 4 years within the annex. So this is not all. This is just a sneak peek, really. So Annex 52 was a collaboration program within a project within the Heat Pumping Technologies Collaboration Program, and the theme was long-term performance monitoring of various types of larger ground source heat pump systems for various use. It ran between January 2018 and December 2021, so it just ended. We were 7 countries participating. It was Sweden who led the project, and the US, Netherlands, UK, Finland, Germany, and Norway, as you see the flags there. We had 3 subtasks that we set out to solve or complete. The first one was to make a bibliography of all the previously published long-term performance measurements of larger ground source heat pump systems that we could find. And then we would add to that individual case study reports on all the case studies that we, or the monitoring projects that we ran within the annex. So that would be the new case studies to add to the bibliography. And based on the experience from the bibliography, we wanted to write a guideline document on how to instrument and measure larger ground source heat pump systems. And based on that, we would then write a guideline document on how to analyze and report the performance of larger ground source heat pump systems. So that's what we set out to do 4 years ago. I had never anticipated that there would be so many countries and so many systems involved in Annex 52, and so many people too. We had 40 running projects, long-term performance projects of larger ground source heat pump system in 7 countries running, but not all of them could complete their measurement programs. Some of it due to the pandemic that just prevented people from getting access to data. But some 30 larger ground source heat pump systems completed their measurement programs. And that's what we have summarized within Annex 52. So as you see, most of them are borehole systems, but we also have examples of groundwater systems and so-called energy piles, and they are spread like this, one in the US and the rest in Europe. And this is another overview of the systems that we measured within Annex 52. So most of them, as you can see, are commercial buildings of various types, but there are also some residential buildings and 1 industrial building. Most of them are borehole systems, but as I said, we also have groundwater systems and 4 energy piles. So why would we measure long-term performance at all? Well, we identified 4 main reasons, good reasons for doing this long-term performance. One is to check design criteria. Another is to detect faults in the system so they can be corrected. Another one is for system optimization and development of components and systems, and also for system benchmarking. So we wanted to cover all these 4 aspects within the annex. So we set out and did this bibliography and literature study. And one thing that struck us was that the nomenclature within performance monitoring is not very consistent. So it's used in different ways. Although I think most people know what they want to communicate, we do not really use the terms and the nomenclature in a consistent way. So for instance, the terms COP, coefficients of performance, is sometimes used, which is really meant to be used for specific lab conditions, specified lab conditions, so we can compare heat pump units specifically. And SEOP, which is a seasonal coefficient of performance, which is the average at several standardized lab conditions that reflect different conditions over a full season, and their corresponding for the cooling side, EER and SEER. These terms were, they are typically made for standards, codes, and regulations, but the terms are often used also for field measurement, although it should really be called performance factors if you do it, if you collect this data from field measurements. So for performance factors, that is the ratio between the delivered heating delivered energy. It could be heating, it could be cooling, or it could be both heating and cooling, and the energy used to deliver it. And it has to be for a defined system boundary and also for a defined time period. And that is surprisingly rarely stated in a clear way in the literature. Also, this may sound unnecessary to point out, but SPF, which is the seasonal performance factor, should be used only for performance factors for a defined system boundary over a full season. It's quite often that it can be seen defined for shorter periods of time than a season, but it's sort of not so good to use that for that. It's better to use it with a monthly or weekly or hourly performance factor. Right. So now, as I said, we have to specify a certain system boundary, and we set out with the SEPAMO system boundary schema that was introduced in 2012 in an EU project, the SEPAMO EU project. They have defined 4 system boundaries, starting with a heat pump and then including larger parts of the system, like the heat source, pump and fan, the backup heater, and then the heat sink, pump and fans that sort of completes the whole system. And that could be used for any type of heat pump system, not only ground source heat pump systems, but it was meant mostly for small single family buildings, so that sort of heat pump system. So it could not really cover the complexity of larger ground source heat pump systems. And another complication was that, as you can see, the system boundaries 3 and 4 were differently defined for heating and cooling mode. And that also complicated things for larger systems that typically or very often can produce both heating and cooling. So we wanted this, we needed to develop this system boundary schema so that it could better reflect the complexity of the larger systems. So this is what we came up with. We wanted it to work both for the typically Central European type with a central heat pump system, centralized heat pump system, but also work for other types like the typically American style distributed heat pump system. So many of us who worked within Annex 52, we were from Europe, so we were always thinking central heat pump systems, but that is a bit too limiting. We have to also have a system boundary schema that works for distributed heat pump system where the heat pumps are located and spread out in the building and not only in one machine room. So we made a schema that has 6 levels. So we added 2. One system boundary is for the ground source circuit itself with its circulation pump. Then the system boundary 1 is for the heat pump, just like the SEPAMO schema. And 2 is also like the SEPAMO schema. It's the heat pump and the ground source. The 3rd level is almost like the SEPAMO, that it includes the tank, the storage tank, but it does not include the auxiliary heating or supplementary cooling, as in the SEPAMO. Then we had a 4th and a 5th system boundaries, which included more parts of the distribution system in the building. And then we had, because for larger ground source heat pump system, you could add supplementary heating and cooling at various system levels. So we didn't want to be restricted to only the 3rd level, system level. You can also add solar heat or cooling or so on different levels of the system. So therefore, we decided to have a mark with a plus sign that indicates where supplementary heating or cooling is introduced at what level. So if I introduce a direct electric heater in the buffer tank, for instance, that would be 3+, and then it would be 4+ and 5+ after that, right? So that's what we came up with. And we also wanted to stress on that the boundary and the time frame must be clearly stated for the performance factors. So seasonal performance factor is the SPF, the monthly performance factor is the MPF, daily performance factor is DPF, and the bind performance factor would be BPF. And bind, that could be like, for instance, you identify the performance for a certain temperature range, for instance, between 10 or 11 degrees, or the performance at that bind level. So we used this system boundary schema and the reasons that we identified for long-term performance and made this matrix for identifying key performance indicators, so that we could see what level are we working on. Is it the ground or the system boundary 0, the heat pump unit itself, which is system boundary 1, or the system level, which could be between 2 and 5. Also, we would find indicators for various use, like, for instance, to answer the question, is it as designed? That would be commissioning. Does it work well? So for fault detection, could this system be better? Could we optimize it? Or could future system be better so we can develop components or system buildups? So, and based on that, here's our short list of identified key performance indicators. So we have 4 fractions of 4 categories of performance indicators for the overall building, for the ground source, for the system level, and for the component level. And this is what we have summarized in our guideline for key performance indicators and analysis. So what did we come up with? Okay, so within 20 minutes, there's absolutely zero chance that I could give you the results from all the 30 measurement projects, but here is some kind of overview. We have identified SPF seasonal performance factors at the 5 levels for the combined heating and cooling. That would be the total system performance factor for only heating only and for cooling only. And as you can see, not all of the systems could measure at every level, every system level, some because they really didn't have all the system levels. So here you can see the number of the projects reporting and how many measured years there are from each system level. In total, we have collected measurement, 119 measurement years, and used that for analysis. As you can see, the SPF has a rather large range, and some of the SPF numbers may seem a bit large, but for those that have very large, we have indicated them with stars or asterisks. That is mainly systems with a high degree of direct cooling or direct heating. Yeah, so I won't go into detail here because we don't have that time, but this is also summarized in our final report. Here is another also picture to just graphically show you the complexity and the large number of measurement years and the level they are. So you can see basically most of them are concentrated around 3, but several of them are above 3 also as a total heating and cooling seasonal performance factor. So the short list of our overall conclusions from Annex 52, 4 years of work, is that ground source systems generally work satisfactorily, but I don't think we found one system that could not be further improved in some way. There's almost always something to do that could twist it to be a little better. Good quality long-term performance monitoring of these large systems is rather rare so far. We have added another 31, but it would be very valuable to do more of it for commissioning reasons, for fault detection reasons, and also for system optimization. We also want to take this opportunity again to encourage you to be very consistent and to clearly state system boundaries and evaluation timeframes, because that is paramount. If you want to compare things and if you want to draw conclusions, you need to show clearly what boundaries and time frames you have been using. There is a need for more frequent uncertainty analysis. Uncertainty analysis have proved to be extremely rare. We did not find a handful even, just a couple of long-term performance measurement with clear uncertainty analysis. We also noticed that missing instrumentation and poor data quality is rather frequently occurring. And that means that the instrumentation and uncertainty analysis guidelines that we have produced within Annex 52 should be rather welcome by the market. And we hope they will be much used in the future. Another conclusion, general conclusion, which we will see more of in the coming presentations, is that minimizing parasitic losses and energy use by, for instance, Legionella protection and domestic hot water circulation and the distribution system in the building will have the potential of improving the performance. I also want to stress on the fact that because we have been many people working on this annex, this is just the core group who have had measurement projects and who have contributed largely to the project reports, the Annex 52 reports, but we have been over 100 people working within Annex 52 over these 4 years. So there is lots of sharp brains and engaged hands that have been working on this. And I'm very grateful to everyone, even those who are not listed, which is actually the majority. So a great thank you to all for that. And with that, I think I will round off and we just notice that for my part, I'm very grateful for the financial support from the Swedish Energy Agency who made this whole thing possible. Thank you very much. I'll now stop sharing and leave some room for questions.
Yes, thank you very much, Singhild, for your presentation. I can see here, I just got a question here. I will read it to you. In addition to ground source heat pumps, an important role in increasing buildings' energy efficiency is the grey wastewater heat recovery. Are you considering an integration of such solution with the European NZ program? For example, additional domestic hot water heating.
Yeah, we had one project from the start that actually had wastewater heat recovery, but it did not complete. It did not complete the measurement programs with the same levels, with the system boundaries and the data quality that was required within Annex 52. We would have very much liked that, but that was one of the projects that fell out. But that would absolutely be useful. It would be one of the supplementary heating sources. So that could be covered with the system boundary schema and the method from Annex 52.
Okay, thank you. Do we have any more questions? Or I can't see any more questions. Yeah, here's one more question here. Now it's coming in. Any vault we can access for the raw data you have used?
Yes, I will come to that in my final presentation later on with the outcomes, but I can mention already now that the results, there are individual reports from all the completed measurement projects available on the Annex 52 website. That would give some of the data, but not the raw data. But we had, as one of the goals within Annex 52, to provide at least one open access raw data set. And we have actually 3 of those raw data sets that can be openly accessed. It's for 2 different systems, one in Stockholm and one in the UK. Both will be presented in the coming presentations, both the Studenthuset and the Hugh Aston building. So these can be downloaded and used for further research and validation and so on.
Okay, thank you very much. Any raised hand? Anyone more who want to pose a question? You can also ask it orally if you want to. I can't see any. Can't see any raised hands, but I have no raised hands. I have a question for you, Signhild, and that is regarding your system boundaries. And within some of the system boundaries, you included the hot water storage tank. So how did you deal with the heat leakage from the storage tank? Did you count this as valuable heat or wasted heat or something in between?
Well, that's one of the reasons we had the system boundaries 3 and 4, right? That we wanted to identify the effect of the buffer tank and the losses from it. Depending on where the buffer tank is located, we could regard the heat losses as useful or not. So we had to look at the system and the location before, and then make a decision on how to classify the heat from that. Okay, one thing more I would like to mention before I leave the floor to the next speaker is that we will now listen to 3 presentations that will be samples of some of the 30 measurement projects that were completed. Also these systems, or the ones that we have picked out for this presentation, is because we want to stress on some certain deliverables from the annex, the connection to some certain conclusions or results from the annex. So they are connected, the selection is connected to that. Also, I want to mention or stress that these systems, the 30 systems that we have monitored, are not selected because they are the best or because they are special or representative or anything like that. They were just selected based on that we could get access to data from them, long-term performance data. So that was so we can't draw any conclusions on whether these are representative or not. They are just a large sample of different system configurations for larger ground source heat pump systems.
Okay, thank you. I just saw some new questions popping up here, and I think we have time for them, so I will read them here. It's SPF varied too much, for example, from 3 to 9, how to explain, how to relate to different locations. You mentioned something, but maybe you can explain again.
Yes. So yeah, that is a very relevant question. The range is because there are so many different system combinations, right? Some of the systems are residential buildings only using heating. Others are, another one is a high temperature storage for an industry. Then there are systems that are using both heating and cooling, and there are systems using more or less only direct cooling. And of course that it makes the variation very large. So it's, depending on how they work, especially you will see the difference between in the cooling mode. If you have a system that works with with only free cooling, it will be a very high performance factor because you only use a circulation pump. But if you use a heat pump in reverse mode, that will take down the performance factor because of the cooling machine, the compressor, that uses more energy for delivering the cooling. So the range is because there are such a variety of system types, and that they work in so different modes. It will be easier to see when you read the reports how they work and why they work the way they do.
Okay, thank you, Signil. It was 2 questions with the same.
Yeah, I saw that.
Yeah. Okay, but thank you very much. I think it's good time now to move on to the next presenter, and that is Dr. Fleur Loveridge, who will give her presentation. So you're welcome to share your screen.
Thank you very much. I think I'm probably going to be touching on some answers to some of those questions as well when we look at the performance factors of these buildings. So my name's Fleur Loveridge. I work for the University of Leeds in the UK. And really today I'm presenting on behalf of the team at Leeds, which includes myself, Simon Rees and Josh Turner. And I'm going to present 2 case study buildings that we contributed to the annex. These 2 buildings are quite different, and we should be able to draw out some different perspectives from them. The first building is called the Crystal, which is a hybrid energy pile borehole ground heat exchanger system. And I will be able to present some information about demand, various seasonal performance factors, and the temperatures within the energy piles during operation, and make some comments about the operating modes and potential implications for control systems for large complicated systems. The second building, the Hugh Aston building, which Signil mentioned, where there is data available already, is a more classic borehole heat exchanger system. And we'll be able to present some data on performance factors, fluid and ground temperatures, and make some comments on the role of heat pump cycling. Then we'll draw some conclusions together from both schemes. So first of all, the Crystal building. This is a building in London. It's a relatively recent building, constructed in 2012. It was a new building at the time for Siemens in the UK, and they developed this building to be very much a kind of a showcase for renewable technologies, and it was therefore constructed entirely off the UK gas grid. It has relatively large heating and cooling demands. This is partly due to its use, so a large proportion of the building was an exhibition centre about renewable technologies. Ironically, that in itself consumed quite a lot of energy, because it had a lot of digital displays and other ICT equipment. There was also conferencing facilities, including a large auditorium, office space, and a cafe. So it's quite a mixed use building. During the time we were monitoring this building, it also changed hands. Siemens sold the building to the Greater London Assembly, and later on in the monitoring period, the use of the building therefore started changing. Our monitoring data is also affected by the COVID period. On the left, you can see a plan of the building. This is the outline footprint of the main building with the energy pile locations beneath it. There's also an energy centre which contained all the plant rooms, and that also has some energy piles beneath it. And then there is a field of borehole heat exchangers in the garden to the building. These were installed to ensure that the entire building could be supplied by, the entire heating and cooling of the building could be supplied by the ground source heat pump system. Overall, there's a length of almost 9 kilometers of drilled heat exchanger supplying the building. The building has 2 centralized heat pumps, each of nominal capacity around 400 kilowatts in heating, and over 600 kilowatts in cooling. The piles themselves are only 20 meters deep and therefore are constructed within the upper geological layers, mainly through shallow gravel layers and clay strata, whereas the boreholes at 150 meters deep move much deeper and pass into the major regional aquifers beneath the site. Thermal response testing from the 150 meter deep boreholes give a conductivity of about 2 watts per meter Kelvin that's likely influenced by moving groundwater, whereas we would expect a lower ground conductivity for the energy piles. However, with a greater number of pipes installed, these might have still a greater heat transfer rate per drilled length. This is a look at the schematic of the system for the building at the Crystal. You can see the two heat pumps in the center. We've got a low loss header on the ground side, 3 circulation pumps operating duty and assist, and 2 circuits related to the energy piles and the boreholes. On the heating, cooling, delivery side, we've got buffer tanks, circulation pumps, and then various different systems for delivery of heat and cool to the building through chilled beams, and also as domestic hot water. There was some additional auxiliary heating supplied by solar thermal, but it made a really very, very small contribution to the scheme of the demands. We've also illustrated on here the boundary levels that we've been able to analyze for this building. In the center, we've got SPF 1, and we put an asterisk against that because it's actually slightly different to the schema that Signal introduced. That's because we could not separate the circulation pumps that were within the heat pumps when we were making these calculations. And then we're able to take SPF 4, which includes the buffer tanks and the circulation pumps here, and SPF 5, which also includes the full demand side infrastructure. First up, we'll take a look at the thermal demand of this building. This should be read in the context of the predicted heating and cooling demands, which were around 300 megawatt hours per year and about 170 something megawatt hours per year cooling. And you can see in these charts that these figures have been vastly exceeded during the actual operation of the building. Things to note also here on this data are that these are annual periods running March to March, as shown in the bar charts. We can also see at the far right-hand side, much reduced demand during the pandemic period when the building was still drawing energy but wasn't actually being used. We can't see it here, but I'm just going to highlight that there was a base load of cooling throughout the year between 20 and 30 megawatt hours per year, and that has an influence on the behavior that we'll see shortly. So first of all, I'll present some seasonal performance factors for these hourly periods. Now, these are seasonal performance factors in heating and, sorry, hourly periods, annual periods, seasonal performance factors in heating and in cooling. We have lots more aggregated data, but I don't have time to present it all now, but you can refer to the report for full details. As would be expected, between SPF 1, 4 and 5, you see a decrease in the values. We can also infer some other interesting trends. So in the first few years of operation of the building, the performance increased. This may be related to a few things, including some efforts to optimize the system a little bit, and also as the building moved from kind of partial to full occupancy. But then we see a substantial decrease in the performance, energy performance of the system with time. We also have low SPFs in the last bars, and that will also be related to the COVID period. But even before that, we were showing a decrease in performance. Now, we can't see it here, but in our kind of monthly and disaggregated data, we can see that typically the performance is worse in cooling than it is in heating. And on initial inspection, it's not entirely unclear why, but when we dug down into the monthly performance factors and looked at the energy demand for all the different pieces of equipment, it appeared that the decrease in performance was related to a change in the way that the system was operating around 2018, when the system seemed to be in cooling mode more often than it was in heating mode, and both the heat pumps came into operation more often. Now, this is a system with nearly balanced heating and cooling demands, but some year-round cooling. This means that in the winter, and then when you're predominantly delivering more heat than cooling, you have higher efficiencies because you're able to recycle some waste heat. But something happened, possibly a change of control system, which meant that some of these efficiencies were lost from 2018 onwards. And we're not a party to all the information related to the control system, but it does appear that something has changed in the operation and how the equipment is operated that has caused this change in performance. So it just highlights that the how you use the system is of importance to the performance that is achieved. We can also look at how much heat was transferred to and from the ground at this site. We can see that more heat is being rejected into the ground than is being extracted from it. This is related to the nature of the loads and the year-round base load in cooling. What also appears to be happening is that most of the heat that's being rejected to the ground is being rejected into the energy piles, and most of the heat that's taken from the ground is being taken from the borehole heat exchangers. Again, this seems to be something related to a control strategy and does not seem to be a most optimal way to operate the system. The result of this is that we can see the temperatures in the energy piles have generally increased during the first half a dozen years of operation. We've got some data gaps. Then we've got some at least partial recovery during the COVID years when the system hasn't been operated so much. So overall, looking at this case study, we can see it's quite a complex system, how it's operated, and the control systems have potentially a large impact on the performance factors that can be achieved. If we turn now to the Hugh Aston building, this is a university building at De Montfort University, but it's mainly a building housing administrative facilities rather than teaching facilities. Interestingly, this is a building with a much larger floor area than the Crystal building. But despite that, actually, it's got about 2/3 of the heat pump capacity compared to the Crystal building. It's supported by 100 boreholes, sorry, 56 boreholes of 100 meters length. So it's about 5.6 kilometers of drilled length compared to around 9 at the Crystal building. And again, it's supplied with multiple heat pumps to supply the demand, this time 4. And if we look at their arrangement, we have the 4 heat pumps, circulation pump connected to the borehole heat exchangers, and the heating and cooling distribution systems with circulation pumps here. So for this building, we've been able to report SPF 1, just the heat pumps, SPF 2 and SPF 4. One of the important things about the data we've been able to obtain from the Hugh Aston building is the higher frequency of the measurements. So when we were looking at the data from the Crystal, we were getting data measurement points every 15 minutes, whereas at the Hugh Aston building, we were able to take data points at every minute, which has impacted the detail of the analysis that's been able to be carried out. So if we look first of all at the overall seasonal performance factors, these are heating and cooling seasonal performance factors. The duration that these have been analysed for are given at the bottom of the chart. So first of all, I draw your attention to the lifetime of the monitoring period on the right-hand side. Again, you can see a decrease as you move from SPF 1 to SPF 4. One of the interesting things to note is that actually these values aren't too dissimilar to the data that was gathered from the Crystal building. But they are quite variable depending on when you look at the data, but in a slightly different way. So at the Crystal, we had increasing performance factors as the system was optimized, and then decreasing performance factors as changes were made again. Here we can distinguish 2 different periods of time when slightly higher and slightly lower performance factors were determined. And we'll dig a little bit more into why that might be. So the first thing to say is if we look at the borehole temperatures and the fluid temperatures, these are daily mean values. So at the top, we've got the borehole fluid temperature in green and the dry bulb in purple. And these all look very reasonable and appropriate for applying good performance conditions. And at the bottom, we have the temperatures in the borehole, the blue lines at 5 meters depth and the orange lines at 10 meters depth. Again, showing very reasonable responses, maybe slight increase again in temperature with time. And that's because, again, this is a system which is rejection dominated. So we're rejecting heat to the ground more than we are extracting it. Now, we don't have the design heating and cooling demands for this building. However, What we can say is that if you calculate the heat transfer rates to the borehole heat exchangers, they are between about 10 and about 13 watts per meter, depending on if you're operating in heating or cooling. And these are quite low. So we have reason to believe that this building actually is probably drawing less energy than was anticipated. So the opposite of the crystal building. But there's nothing here that leads us to think that the ground heat exchanger is the cause of the differences in the performance factors. However, if we look at the performance of the heat pump itself, we start to get some more interesting information. So this chart is plotting the percentage difference between simulated and experimental load heat transfer for the heat pump. So what's happened here is that we've looked at how the heat pump should be performing and compared it to the idealized product information. And then we've plotted that against the cycle time for the heat pump. So how long it's cycling between on and off. And if we look at the trend plotted to this, if they have a cycle time of more than 15 minutes, then the heat pump model is within 10 or 15% of what we would expect from the manufacturer's information. Whereas if the cycling time is less than 5 minutes for the heat pump, then we're looking at more like 25% reduction in performance compared to what would be expected by factory conditions. If we look at this in terms of binned hourly performance factor for cooling, so we should get our wrist slapped here because it says SPF, but actually this is hourly performance factor in cooling. And this has been binned according to the cycle time. So I'm just going to draw your attention to the blue bars in this chart. This is for the cycle time of less than 10 minutes. And this peaks in the performance factor between 2 and 3. If we look at the yellow and the orange bars over here that are peaking at performance factors between 4 and 6, and these are cycle times greater than 40 minutes. So essentially, this is just really showing how the best performance of the system is really associated with the largest cycle times for the heat pump. Finally, I'm just going to draw a few things together from the different case studies I've presented. So in both the buildings that we've studied here, they both have favorable monitored ground and fluid temperatures where we have the fluid temperatures, but we do see some increase in the temperatures in the ground heat exchangers with time due to the dominance of heat rejection to the ground in both these systems. It appears from what we can tell that both these ground loops may be over-designed. At the Crystal, they still seem to be performing well, despite the fact that the building loads are much larger than anticipated. At the Hugh Aston building, there's reason to believe that actually the building loads are less than anticipated and the heat transfer rates to the ground are very low. At the Crystal, we have reason to believe that the operating mode or the control strategy that's influencing the operating mode is definitely influencing the performance of the system. It appears that the boreholes and the piles are being used differently. And if this were not the case, that would probably lead to enhanced performance. And similarly, there's been some changes in the way that the system operates and the increasing dominance of cooling modes since 2018, which means, again, there's been a decrease in performance after that time. This is something we're trying to get to the bottom of at the moment, but we've been hindered in getting follow-up data by the pandemic and the change of ownership of the building. Finally, the Hugh Aston building has given us a really lovely illustration of the importance of minimizing cycling of heat pumps to increase performance, and how the longer you can have those cycling times, the higher the performance factors you're going to be able to obtain for your system. Signa's already mentioned that it can be quite difficult to obtain high quality long-term performance measurements of buildings. Therefore, I've actually got quite a large number of people I need to thank for contributing to obtaining the data we have. The data we have is not perfect. There are limitations of it in many places, but the help of a lot of people has been required along the way. So as I mentioned, thanks to Simon Rees and Josh Turner for their contributions to all the data analysis shown here. We've received funding to participation in the annex from Bayes, and staff time has been funded by Engineering Physical Sciences Research Council and Royal Academy of Engineering in the UK. There's also a stream of building owners, contractors and consultants who have assisted us with data along the way, and the Research Council, William Parry and Harvey Skinner at the University of Southampton, who contributed to getting the pile temperature measurements in place at the crystal. So thank you very much, and happy to take any questions.
Thank you very much for your presentation. I can note that we have received some questions in the chat here. The first question is, at the mentioned cooling powers, considering the hourly variations of the building's cooling loads, did you analyze the use of ice banks to flattering the overall electric power consumption peaks?
I think I might need a little bit of clarification on that question. Is the ice banks referred to a facility of the building, or is that an analysis technique? Because it's not something we've done.
Yeah, could you give some clarification to that question? Either in the chat or okay, you can write your clarification here in the chat.
Hello.
Okay.
Yes,
yeah, welcome.
Just to clear up the ice bank, it's a latent energy storage system, very common in cooling, high power cooling systems. When by night, the water contained in the system is transformed into ice, and the energy, latent energy, is used by day when the cooling load necessary to the building is very high. So it's possible to flatten a little bit the electric energy consumption, and to improve quality of cooling, at least by day when the necessity is very high.
Okay, thank you. I thought you might mean something like that. So obviously, we have not been involved in the design or the setup of any of these systems. We've kind of taken the opportunities to gather what data is available, and strategies like you mentioned are obviously very sensible approaches, but there was not such a system in place at this building, or either of these buildings.
The question is not meant for the past or for the present. It's meant for the future, for the development of this. It's not a question referring to what you did, because you did the best possible for this stage of development of heat pumping. But it's necessary to combine a little bit concepts due to the necessity to improve energy consumption and energy utilization. When producing electric energy, it is very uncomfortable to increase by day the production and not to have consumption by night. There are countries, Switzerland, for example, where above 50 kilowatts, such latent energy storage systems are compulsory.
Yeah, no, I mean, I totally agree. And one of the things that the Crystal building does quite well is that it does utilize the waste heat from the base load cooling to improve the performance factors of the heating during the winter months.
Yeah, you're right. Thank you so much anyhow.
Thank you.
Okay, thank you. We go on to the next question here. Can you elaborate on the cycling performance? When does the short 10-minute cycle occur as compared to the longer 60 minutes ones?
So I believe it'll be about the variability of the demand. I'm also going to cross-refer this question to Simon Rees if he is still on the call. I saw he was here earlier, and he might be able to give a more specific answer, whether it was particular times of day that was the case for.
Yeah, I think
I can see Simon's unmuted himself.
Yeah, could you please clarify on that, Simon?
Yeah, it's quite simple, really. The short cycles are basically where the system demands are low. So, I mean, in that particular building, there were some spaces with cooling that were operating 24 hours a day. So like computer rooms for students. But when that was the only thing operating, the load was very low. But the whole system had to keep operating. So you end up with short cycling.
Thank you, Simon.
Okay, thank you. Then we have another question here. Although heat reaction is higher than heat extraction, the SPFs are low. Does that have impact on project economics?
So clearly, your seasonal performance factors are going to impact on your operating costs, basically. Now, in the UK, we've traditionally had quite a high ratio between electricity and gas costs. And that's why probably we've not deployed as many heat pumps as other parts of Europe. Now we're in a situation where that ratio is about 3, sometimes a bit less than 3, which means that heat pumps should be cheaper to operate than alternative gas systems. But obviously, what factors you're actually achieving in your performance are going to impact that. And that's why it's really important to gather this data and understand why, if performance factors are low, that is the case, so that we can work to improve them. It's clear from the information at the Crystal that it has been possible to influence the performance factors by adjusting how the system operates. But if we don't gather information on it, we can't learn these things and make those adjustments. So yeah, absolutely, it affects the economics, and we all need to be promoting the findings of this annex and the instrumentation and monitoring guidelines to ensure that we achieve the design performances we're looking for, essentially.
Okay, thank you. Another question here in you, Aston. What is the temperature departure into the heating and cooling emitters? Have you analyzed to which extent it impacts the heat pump performance factor?
So my understanding here is that the primary factor influencing the heat pump performance was the issue of the cycling, essentially, and that was the most important one. Again, if Simon would like to add anything, then I will defer to him to do so.
Yeah, a couple of things. So the heating supply temperature was 55 centigrade. So it could have been designed for a lower temperature. But in the data where we compared, that you saw Fleur present, where we compared the performance versus the theoretical performance, then that sort of temperature effect was taken into account. In other words, we know the cycling is more important than the temperature.
Okay.
I think the next one might be for you as well, Simon, so hold on.
Yeah.
So what was the next question?
No.
I
think no, it was not more. It was just you who commented. You added an additional
it's Simon's comment. Okay.
Yeah. Yes. Okay. So I can't see any more questions here. And do we have any no raised hands as far as I can see? So thank you very much. And I think we leave the floor to the next presenter, Dr. Saqib Javed.
Thank you.
Are you ready to share your presentation, Saqib?
Yes, I am. Does it work?
Yes, it works fine.
Perfect. So firstly, thanks, Caroline. As you have mentioned, my name is Saqib Javed, and I am working as associate professor at Lund University. And this project was carried out when I was also working at Chalmers, University of Technology in Gothenburg, Sweden. The title of my presentation is The Performance of a BTS System with Direct Heating and Cooling in the N3 Lindhagen building in Stockholm. The case study is a commercial / office building complex located on the island of Kungsholmen in central Stockholm. The building has 9 office floors and 3 basement parking levels. One part of the building, it houses the headquarters of Skanska, which is a leading property developer who were also the project partners and provided data for this study. The building was taken into operation in 2014. It has a net floor area of approximately 65,000 square meters. So it's a large building complex. And the space and process cooling demands of this building are met entirely by a passive cooling system, which comprises a direct ground cooling system, which is called deep green cooling by the developers. The deep green cooling system, it consists of 144 boreholes, double U-tube, each being 220 meters deep. So this is approximately 30 some kilometers in depth in total. We have 5 years of monitoring data for this project. This figure shows a simple schematic of the system and the principal instrumentation used for the measurements. The temperature measurements were taken using 29 temperature sensors. The temperature sensors were of PT100 and PT1000 types with an accuracy of better than 0.5 kelvins. There were differential temperature measurements, which were taken using matched pair of sensors with an accuracy of better than 1.7%. The flow meters in the fluid circuit were of ultrasonic type with an accuracy of more than 5%. The airflow measurements in the AHU were taken using a pressure differential based flow measurement system, and it had a tolerance of about 4%. The heat transfer rates were measured using heat flow meters with an accuracy of more than 1%. The electric consumption of all the pumps and the fans in the AHU were measured individually using meters with an accuracy of more than 1%. So it was a lot of instrumentation and good instrumentation which was installed in this building. The borehole system, which is shown here in green, was coupled to the cooling and preheating system of the building via 2 separate heat exchangers. The borehole system, it provides high temperature chilled water at about 16 degrees to the passive chill beams installed in the building for space and process cooling. The borehole system also served the cooling coil installed in the AHU for air conditioning the incoming ventilation air. The cooling system also includes an ambient air cooling coil installed in the AHU to exchange the heat energy between the building cooling loop and the incoming ventilation air. When the outside temperature was below 20 degrees, the return water from the building cooling system was cooled by the incoming ventilation air. The ambient air cooling system thus provides passive cooling to the building while simultaneously providing air conditioning to the incoming ventilation air. The borehole system was also connected to the preheating coil in the AHU. When the outside temperature was below 15 degrees, the ventilation air was preheated by the borehole system. Preheating the ventilation air helps the ground to be thermally balanced over the years by minimizing the long heat term buildup in the boreholes. The space heating and hot water demands of the building were met with district heating. Space heating to the building is provided by a low temperature radiator system. The hot water for domestic purposes is supplied through a separate heat exchanger, and the hot water from district heating is also supplied to the main heating coil in the AHU for heating the ventilation air when needed. However, preheating the ventilation air by boreholes or by ambient air cooling coils, together with the heat recovery in the AHU, generally decreases the amount of heating energy needed by the main heating coil. So one of the first and main challenges for this study was how to define the system boundaries due to the absence of any heat pump in the system. And this basically meant that the Annex 52 system boundaries were not readily applicable. After some thinking, the system boundaries shown in this figure were chosen. The inner boundary, which is SPF 0, it only covers the ground source. It considers the thermal energy injected or extracted from the ground and the electrical energy consumed by the borehole side circulation pumps. The outer boundary, SPF 5+, it incorporates the entire passive cooling system, including ground cooling and the ambient air cooling. It considers the cooling energy supply to the building, the preheating energy for the ventilation air, the electrical energy consumed by all circulation pumps in the passive cooling system, and the part of electrical energy used by the AHU fans to overcome the pressure drops of the preheating, the ambient air cooling, and the main cooling coil in the AHU. This choice was, however, very subjective, and we made it to keep the purchased electrical energy separate from the thermal energy from the district heating system. The heating energy supplied to the building by district heating, the thermal energy recovered by the heat recovery system in the AHU, and the electrical energy consumed by fans and pumps for these processes were not considered when finding out the seasonal performance factors. This figure shows the daily mean outdoor temperature and the fluid temperature supplied by the borehole system. The outdoor air temperature, as can be seen here, it varied from between -10 to above 28, 29 degrees during the measurement period and had typical seasonal variations. The supplied fluid temperature from the borehole systems were around 16 degrees in summer and around 9 to 10 degrees in winter. The supply fluid temperature in summer were lower than the outside air temperature, and in winter were higher than the outside air temperature. So it made a lot of sense to use such a system. This figure shows the borehole supply and return temperatures, and it can also be seen that the temperatures have remained quite steady over several years. This implies that the ground heat injections and extractions have been well balanced over the measurement period. This figure shows the MIAD energy signature of the building. The peak heating loads are around 3,600 kilowatts, and the peak cooling load is approximately 1,300 kilowatts, and is quite low compared to the peak heating demand. So in reality, the building is a heating dominated building, but they have designed a separate system for the cooling part of the building. The thermal energies needs for the building are shown in this figure. In winter, the thermal energy delivered to the building is mostly from AHU heat recovery and district heating, shown by dashed yellow and red lines here in this graph. The ground preheating, which is shown by the red solid area, has a rather small share in the supplied heating energy, even in winter. In summer, the thermal energy needs of the building are significantly lower than the heating season. Here it can be seen. The direct ground cooling and the ambient air cooling constitute the largest shares of delivered thermal energy to the building in summer. To have a better view of this delivered energy, this figure shows the percentage share of the delivered thermal energies. We can see that, especially for cooling, all the cooling in autumn, in spring, and in winter is provided by the ambient air. Or should I say, most of the cooling. In summer, the delivered thermal energy is dominated by the ground and ambient air cooling. Under peak conditions, peak summer conditions, the ground cooling covers up to 90% of the delivered thermal energy to the building. Now coming to the electrical energy use of the building, this figure shows the electrical energy use of fans and pumps in the HVAC system of the case study building. The first thing which we can see is that the purchase energy required for delivering the thermal energy is significantly lower than the amount of delivered thermal energy. There we had a scale of up to 1500 megawatt hours, and here we only have 50 megawatt hours. This figure shows the percentage plot of the electrical energy used. So the first thing to notice is that the AHU fan energy, it accounts for over 2/3 of the total electricity consumed by fans and pumps in the HVAC system of the building. And over 70% of this energy is consumed by the AHU fans to overcome the pressure losses of the heat recovery system and for the duct supply system. These components, however, are outside the system boundaries we have defined. Within our system boundaries, the largest portion of the fan energy is consumed to overcome the pressure losses of the ambient air and the ground cooling coils, respectively. The largest part of the pump energy share, shown as dashed blue lines here, is consumed by the circulation pumps in the cooling circuit, especially by the circulation pumps serving the active chill beams. The fan and pump energies for preheating systems are comparatively lower than those of the cooling system. This figure shows the same data, but in GLE format. It can again be seen that the delivered energy magnitude is several folds higher than the electrical energy consumed to deliver this energy. So we have a scale of about 9,000 megawatt hours for heating energy and about 1,500 megawatt hours for cooling energy. And the supply or the electrical energy used to deliver this is approximately 300 to 400 megawatt hours on this scale. So it's significantly smaller. Coming to the performance results, this figure shows the monthly performance factors in the cooling mode for the ground part. So it can be seen that the performance factors, they vary mostly between 100 and 150. In the preheating mode, the performance factors are again very high and again vary between 100 and 150 in general. Just to highlight, when finding the monthly performance factors for the ground, only the delivered energy from the ground and the pumping power in the borehole circuit was considered. Now coming to the system performance factor, the MPF 5+. For the cooling part, it is generally between 12 and 18. And when finding the cooling monthly performance factors, we consider the delivered energy And on the electrical energy, all the pumps in the borehole side were considered. All the relevant pumping power for the distribution system was considered, and the fan energy consumed by or used to overcome the pressure losses of these different heat exchanges in the AHUs were considered. For the preheating monthly performance factor for the boundary 5+, again, the performance was relatively good. It was mostly between 30 and 60. Again, all the energies for the fan and pump were considered for the applied system boundary. If we have to summarize these results in GLE values, we can see that the annual SPF 0 for the cooling mode was between approximately 119 to 145, which is a very high number. And for the preheating mode, it was between approximately 100 and 135 for the borehole system boundary. For the entire system, the performance of the cooling system was between 15 and 20. And for the heating system, it was between 39 and 52. So we got extremely high performance factors for both preheating and the cooling part of the system. To show how much heat was injected or ejected from the boreholes, I have a few more slides here. The first slide shows the heat transfer rate. In the cooling part, the heat transfer rates were about 35 watts per meter. And for heating, it was generally around 20 watts per meter. The system was adequately designed, as the heat transfer rates were not very low, neither very high. And in terms of the balancing, this slide shows that although there seems to be some imbalance for some years, but we have to remember that the seasons are, the winter season is divided between 2016 and 17. So if you look at it from a seasonal point of view, the ground heat balance was really good. The amount of heat injected to the ground was mostly taken out the next year. To conclude my talk, we considered a unique direct ground cooling and preheating system for our analysis. And the choice of the system boundaries was subjective. Of course, we could have defined the system boundary, especially the system boundary of 5+, in a different way. But we have our own reasons for separating the electrical energy and the thermal energy provided by the district heating into two different systems. And then the fan energy consumption was divided into electrical energy expended for preheating, for ambient air cooling, for the heat recovery, cooling, and the ventilation process based on the measured pressure drops. For the performance in the cooling mode for the borehole part was between 119 and 145, and for the heating part was between 102 and 136. For the system part, for the system perspective, the SPF was between 15 to 20 for cooling, and for preheating was between 39 and 52. The SPFs were quite high, and they were even higher under peak demands. This is one thing we noticed, and this we thought was because the pumps and the fans were operating more efficiently when they were running on actual design conditions. The SPF 0 and the SPF 5+, they mainly differed due to the energy consumption of the distribution system. And in terms of the energy use, the fan energy for coils and pump energy for cooling distribution was among the largest contributors for the system. This work has been presented by me, but my colleagues Hao and Hongai, they also helped a lot in analyzing the data. So I would also like to acknowledge them as well as Skanska for providing the data. I think we have some time for questions or your comments.
Yes, thank you very much for your presentation. We have received some questions here. The first question is that we see a similar drop of performance after the first initial years. Do you know why?
You have to elaborate this question. I really don't. We see the similar drop of performance.
Yes, I can elaborate. I was thinking as similar as with other presentations today. They had a similar kind of peak after a couple of years, and then they kind of dropped. And the others commented that they considered this might be due to some change parameters on how the system was run or optimized. Do you know if that's the case here as well?
Okay, so for the first year, 2014, I would say that this was the period when the building was being optimized for the system. And that was why the performance is slightly different from the remaining years. I don't see any drop of performance because the temperatures have not changed. So it's just more the system adjustment, which might have caused the first year to be different than the other years.
Okay. Okay. Thank you.
You're welcome.
Okay, then we have the next question here. The overall efficiency of any ground source heat pump system is overwhelmingly related to the thermal sizing of the building's interior terminals. The more generous the indoor heat exchanger surfaces are, the lower heat pump system required parameters are, obviously increasing so the performance coefficients. Are you considering extending existing studies to include and optimize these dependencies?
Well, the first thing is that we are not designing the system. We have just analyzed the system here. All the case studies being presented here are only analysis of the data. So we were not the engineers behind these projects. We have all our opinions how these systems could have been designed. But for this particular case study, they actually extended the heat transfer area in the building by installing large size chill beams. And that was why the system actually works. Because if you don't have that, then it will be difficult to provide sufficient cooling with the given temperature conditions. So they actually did design the system based on enhanced heat transfer areas in the building.
Okay, thank you very much for your answer. The next question here is, what is the LCC, the life cycle cost of this system?
Well, this is a very interesting question. Of course, for this particular building, we were not shared. We were only given data for the thermal performance and no costing was shared. But I have a colleague, I think, who was also in the audience, Taha, and we have been doing some LCC comparison of this type of system compared to a ground source heat pump system. And we have seen that there is no clear answer of which system has a better LCC. In general, if you have a balanced heating and cooling demand, then a system like I have shown you tends to show slightly better LCC than a traditional ground source heat pump system.
Okay, thank you for your answer. The next question I see here is, were indoor climate cooling set points always met? Did the system work?
Yes, the thermal comfort was always achieved. It worked.
Okay, thank you. Do we have time for some more questions? If I couldn't see any more questions in the chat. Anyone who has would like to raise their hand and ask a question? Okay, I can't see any questions? So thank you very much for your presentation. And I think we move on to the next presentation by Dr. Jeffrey Spittler. You're welcome to share your screen.
Okay, hello everyone. I'll say, since I'm giving this from Oklahoma, good morning. I'm going to talk about a couple systems, one in Atlanta, Georgia, and the other in Stockholm in Sweden. A little bit of a comparison between the systems, although it's anecdotal because there's one system in each location. So there's two systems types here. We have a centralized system and a distributed system. So the centralized system is what I think of as a typical European system. We've got heat pumps that are in a central location in a building mechanical room. Then we distribute hot water and chilled water around the building. In the mechanical room, we have water-to-water heat pumps, and for heating, we use panel radiators, and for cooling, fan coil units. Would be typical. Of course, you can have embedded tubing for heating and even for cooling, but sort of typical system. This is how I view it for a European system. And then in North America, we do have central systems, but I think much more common for ground source heat pump systems are distributed systems where we have water to air heat pumps distributed around the building. And instead of piping hot and chilled water, we have ambient or ground temperature water being distributed, being provided as the source or sink for each heat pump. And then for heating, right, we have hot air and with ducts, and the fan is integral with the water to air heat pump. And for cooling, we've got cold air being distributed. So the annex, we found early on, Singhild and I did a fairly extensive literature review, found that the ways that system performance was reported in literature were both disparate and inconsistent. So we would see different definitions. Oftentimes there's no discussion of what the boundaries that are actually being used are, and just found it somewhat confusing. So we hope that one thing Annex 52 did is improve the terminology and also give an improved way of handling the system boundaries. So earlier SEPAMO was mentioned, which was mainly aimed at residential systems. And our boundary schema that we developed is to some degree an extension of the SEPAMO schema, but it's intended to be suitable for commercial systems. And I think that's one of our major contributions for the work of the annex. So for a centralized system, you've now seen this sort of thing several times, but we have a boundary just for the ground heat exchanger, for the heat pumps by themselves, for the heat pumps and ground heat exchanger combined, and then separate heat pumps that treat any storage. So if we have loss from the storage or something, it would be treated at this boundary condition. A boundary that covers the distribution energy to the say fan coil units or panel radiators. Then in the case of fan coil units that have consumed power at the terminal unit, that would be this boundary level 5. So this, I think the schema works pretty well for a typical centralized system. So for a distributed system, we have a few challenges. The schema still works, but it's not convenient to measure at every level. So for a distributed system, which you see multiple water to air heat pumps shown schematically here. So there's 3. We have a 0 level boundary around the ground heat exchanger. We have a level 1 boundary around the heat pump, but generally speaking, unless you measure the fan power separately, it's really difficult to make this measurement. So if you don't make internal measurements in each heat pump, you can only measure boundaries 0 and 5. But at least we have I'll say a way of defining the boundaries so we can make comparisons with other systems, and I hope clarify what the differences are. So I have a tale of two systems that we're going to look at. So one is a centralized system at the Studenthuset building in Stockholm. It's a university building. The climate in Stockholm, of course, is cold and humid, and the undisturbed ground temperature is somewhere around 8 degrees Celsius. And then in the other system, a distributed system, is at the ASHRAE headquarters building in Atlanta, Georgia. Actually, the former ASHRAE headquarters building. It was sold by ASHRAE to a hospital complex that had surrounded the building. And Atlanta, if you haven't been there, it's a hot, humid climate. The undisturbed ground temperature is close to 20 degrees C, so it's quite a bit warmer. And the photo here, this is the mechanical room for the Studenthuset building. So you can see several heat pumps lined up here. And this is well, we could call this the mechanical closet for the distributed system at the Atlanta headquarters building. So they put a glass door on the closet that holds the circulating pumps and distributes the ambient temperature level water from the ground heat exchanger to the heat pumps. Okay, so the Studenthuset building is about 6,300 square meters of floor area. It's got 5 40 kilowatt ground source heat pumps that provide both building heating and domestic hot water. There's 20 boreholes. The heat pumps only provide heating. The building does use cooling, or what's commonly thought of as free cooling. So fluid from the ground heat exchanger is just circulated through the cooling coil in a fan coil unit or multiple fan coil units to provide cooling. So we don't have to use a vapor compression cycle for that. One feature of the Studenthuset is that it has a Legionella protection system that continuously circulates fluid around the building. So if you go to any bathroom in the building and turn on hot water, the water you'll have hot water nearly instantly. And the heat pumps provide hot water at 55 degrees Celsius, and there's a separate electric resistance heating, a separate tank for domestic hot water that raises temperature to 60 degrees Celsius. The system's got hydronic, or what we call hydronic distribution. So we're again circulating chilled water and hot water around the building, and fan coil units and panel radiators. And we have actually 5 years of data that we've collected. So we have several papers starting with 1 year of data, and then I think 3 years, then final 5 years of data paper. Okay, this plot shows the 5 years of data, with the green being the return temperatures from the ground heat exchanger, and the blue actually being the hourly air temperatures outside. And this is part of the story we often tell about ground source heat pump systems, that the temperatures are more favorable. So, in the summer when it's hot outside, we have relatively cool fluid coming back from the ground heat exchanger. In the winter when it's cold outside, we have relatively warm fluid coming back. And that is part of the story, but maybe not the biggest part of the story. So have to skip over a lot of details about how we made the measurements and how we calculated the uncertainty and so on, but I will try to explain this figure here. So what each group of bars here on the left are at different levels. So this is level 1, which is just the heat pump, and level 2, which includes the source side circulating pump, and level 3, which includes the Legionella protection system, and then finally level 5, which includes the load side circulating pump. So on the left-hand side, we have heating, and you can see that the heat pumps themselves have a seasonal performance factor of around pretty close to 4, between 3.5 and 4 every year. And there's 5 bars here, 1 for every year that we measured the performance. But what you can see is that well, there is some energy used by the source side circulating pump, which drops it about to 3.5. This Legionella protection system drops the performance down to about 2.5. And unfortunately, the load side circulation pumps drop the performance factor to about 1.5. And while you could say that the ground source heat pump systems works, or at least the ground source heat pump portion of the system works pretty well, we see that there's pretty high energy consumption and hence high decrease in performance of factors, decrease in the performance factors due to different things, but there's pretty large jump just due to the distribution energy. So in my view, this is a sort of fault of the overall system, that this energy is quite high. And so the performance factors are really, really lower than desirable. Now for cooling, we have this free cooling system. So if you look here, this is level 2, right, which just includes really in this case, it just includes the circulating pump because there's no heat pump providing cooling. You can see it varies over the years, but this is 45, about the highest. It varies from around maybe 32 or 33 to 45, right? That's fantastic, much better than any heat pump would give you, because this free cooling is great. Unfortunately, when you include the effect of the load side circulating pumps and the fans, the SPF drops. I know it looks like it goes up, but this is 45 right here, and this is 3 here. So the cooling, surprisingly, here, we can compare this to the ASHRAE headquarters building in Atlanta. If we can count the distribution energy, it's okay. It's not bad, 3, but it's not super high like we might have expected when we were looking at values of 45. Okay, so earlier the presentation, particularly by Fleur, highlighted the effect of cycling on their system, which was a centralized system. This centralized system also shows what we might call part load effects. And this plot here is a plot of the daily performance factor in blue, red, or green versus the total daily heating cooling provided. And the red is mainly heating, and the green is where it's providing both heating and cooling, and the blue is mainly cooling. So you sort of see different trends depending on what's happening, but in every case, the performance factor increases when the load gets higher, right? And that's because different sort of cycling losses and other parasitic losses. I'll come to these in a minute, but they all have an impact. So we get much better performance on days when we have a lot of heating or days when we have a lot of cooling. In fact, you can just see this really start to climb if we have a lot of cooling. It gets over 5, but unfortunately, there's not that many days when we see that much cooling, so we don't see a lot such high performance factors on average. So just a comment on the student Huset then, the ground source heat pump itself, or the ground source heat pumps themselves, work quite well, right? The owner's actually quite happy with the overall system performance, but the performance factors, once we account for distribution losses, are, in my opinion, low. And I guess I think it depends what we're after here, whether we think this is good news or bad news. If we're solely interested in showing that ground source heat pumps work well, I suppose it's good news. If we'd really like to reduce the overall building heating and cooling system energy usage, and I think we probably need to do some more investigating on the rest of the system. Okay, so the actual performance, I'll say it's counter to thermodynamic expectations, right? We expect, maybe didn't show this as clearly as I might if I had more time, but from a thermodynamic standpoint, we expect when the temperature coming back from the ground heat exchanger is really low, we should get very high cooling performance factors or higher cooling performance factors. Or when the temperature coming back from the ground heat exchanger is warm, we should get higher heating performance. And we really don't see that. What we really see is this: the more heating, cooling we're providing, the higher the performance, right? And the reasons in this building that the actual performance is more dependent on the load include the Legionella protection system and the load side distribution system, also the source side circulating pump. all these things consume power that's not completely proportional to the amount of usage. So when we don't use very much, these energy losses have an impact. There's also cycling effects on the heat pumps, and there are other parasitic losses. So, every modern heat pump has a control board that runs all the time that the heat pump's on. And if you're not using very much heating, it has a detrimental effect on the performance factor, or not much cooling. And then sometimes heat pumps have, say, solenoid actuated valves that are on even when the system's off, or if we get to the distributed system, it runs fans. The fans sometimes run when the compressor's off. So if we now switch to the ASHRAE headquarters building, this system was actually part of a ground source, air source comparison project. But I'm really only going to talk about the ground source today, except for maybe I'll just say it did outperform very much the air source heat pump system. So the ground source heat pump system served mainly the second floor. It's about 1,445 square meters. Building was renovated in 2008, and our data collection analysis took place from July of 2011 through June of 2013. So we have 2 years of data on this system. It's got 14 water to air heat pumps with 119 kilowatts nominal cooling capacity and 12 boreholes 122 meters deep. Okay, so I've tried to make the presentations of the two buildings somewhat parallel. These are the return temperatures from the ground heat exchanger, shown here in blue when it was cooling dominated and red when it was heating dominated. So you see most of those symbols are blue with a little bit of red in the winter. And then the green are hourly air temperatures. So again, it gets a lot colder than the temperature of the ground, and in the winter and in the summer, the air outside gets a lot hotter. You might note that the scale here is -10 to 40 Celsius. So these are the seasonal performance factors only at level 5. I'll show you some level 0 results, but we didn't measure the fan power separately, so we couldn't give very well, say, a level 2 performance factor. So one interesting thing here is in the first winter of operation, this would be July 2011 to June 2012, so it covers the whole winter. The performance factor for the heating was about 2.7, and the next winter was about 3.5. This was due to one simple change in the controller set point for the pump speed. I'm going to skip over the details of how the pumping system works. I'll just say that it adjusts the speed to maintain more or less constant flow in each heat pump. So when we have fewer heat pumps that are running, we have a lower overall system flow. Right? But you can see this change I'll just say mainly due to this change in the pump setting. So we lowered the flows. Actually, the ground source heat pumps themselves had actually lower performance, but the overall system performance was higher. And this is, it's not just the heat pump, there's the rest of the system that's important too. Cooling, we saw maybe just a little bit difference, not quite as big, but about a factor of went from about 3.8 to maybe 3.7 to 3.9, something like that. If we plot the monthly performance, that's for heating, for the ground source heat pump, that's in blue. I mentioned there was an air source system. You can see it had substantially lower performance factors for both this first heating season, the first cooling season. There's a reason why we couldn't measure its performance beyond that. So we only have the sort of fair comparison for this first time. Okay. So a few other things. I mentioned the controller issue. One thing that performance measurement can do, if it's analyzed sort of on an as-you-go basis, is detect faults. So this system actually at one point had a heat pump with a stuck reversing valve. So that particular heat pump unfortunately served the stairwell, where I guess people don't necessarily expect to have much thermal comfort. So it was just operating without providing heating or cooling. This particular plot are bin performance factors for cooling and versus the heat pump entering fluid temperature. And the green is what we got after we fixed that stuck reversing valve. And before it was fixed, you could see that it had just that one heat pump consuming power without providing heating or cooling was actually pretty serious detriment to the overall system performance. Okay, again, the parasitic losses or part load effects and things are important. Here's the daily performance factor for both heating and cooling together at level 5 versus the total daily heating and cooling provided. And as you can see, when you have very low heating and cooling required, right, the system performance factor is low. As that increases, as the total daily heating and cooling increase, the performance factor increases. So we get quite good performance when we have the highest load days. And when we have low load days, well, the fans run and the control boards run and so on. They use energy, but it's not providing much heating and cooling. And one of the things we did introduce this boundary level 0, which is just the ground heat exchanger. I don't think there's been a lot. I've not seen any published data on this. So this is, I've taken this and done a weekly performance factor for the system over a 2-year period. And this blue line here is where we changed the control set point on the differential pressure control. So the pump control was changed. And if you just look, you can see there's a big change here in the performance factor, which is what we'd expect. I don't have a separate measurement to give you a detailed comparison showing the heat pump performance dropping some. But again, overall, the system performance changed. But sort of here's a first look at what a performance factor for the ground heat exchanger might actually look like. Okay, so to again give some comments on the performance, overall the system performance level 5 seems quite good. We got significantly better performance than the air source heat pump system. In a building, this building had a quite knowledgeable owner and maintenance staff, and even with that, this maybe poor choice or non-optimal choice of set point went unnoticed for 4 years. Stuck reversing valve went unnoticed for several months. So I think one of our findings of the whole annex is that no matter how good the ground source heat pump system is, there's usually some room for improvement. Again, the actual performance is counter to the thermodynamic expectations, right? And some of this is due to the load side distribution system. So the fans run all business hours. And if there's no heating or cooling provided, the fans just circulate air. So again, it's an energy usage without providing heating and cooling. Cycling effects, and then other parasitic losses. So even the control boards have an effect on the overall system performance. Okay, so how meaningful are our results? Is one system really better than another system? How should we specify our instrumentation? These are all questions that can be partly addressed with analysis of uncertainties. And I know for many people, uncertainties seem rather maybe esoteric, academic in nature, but it's something that's considered early on in the design. It should lower the overall cost to get good information out of the system. So I don't plan to spend time going over how to calculate uncertainties, but one of the things we did produce is this guideline document on calculation of uncertainties. And it's available on the website, the Annex website. So my conclusions are that we've found the Annex 52 boundary schema and the guidance provide really powerful tools for analyzing system performance, comparing results between systems, for benchmarking and diagnosing faults. And I think we envision a future where performance monitoring is ubiquitous. It'll be common. The Internet of Things is lowering costs, and we think not only is it a powerful tool, but it can be used to reduce the overall energy consumption of all kinds of systems, not just ground source heat pumps. Okay, by way of acknowledgement, the ASHRAE headquarters work was originally funded by the Geothermal Exchange Organization here in the US. We had some support from the Southern Company and a lot of support from ASHRAE, from particularly Mike Vaughn, and also the OG&E Energy Technology Chair. For Student Huset, my co-investigator was the leader of the annex, Singhild Jalin, and we also had a significant help from Anders Larsen and Åke Ansberg at Akademiska Hus, who graciously provided the data and also graciously allowed us to provide it in open repository. So you often find building owners are reluctant to have data shared about their building. It might be embarrassing or it might reveal business secrets. And we have 2 data sets that are freely available. So, and then finally, at the end of the presentation slides, which I think will be available, there is a list of references here. So I thank you very much for your time, and I'll be glad to take questions. Let's see if I can stop sharing my screen. Carlin, do we have any questions?
Yes, we have. Thank you very much for your presentation here. The first question is, were both the Stockholm and Atlanta heat pumps variable controlled?
Yeah, that's a good question. The Atlanta heat pumps are 2-stage, right? So the compressor and the fan operate on a 2-stage basis. So when you deviate a certain amount from the set point, it comes into first stage operation. And then the second stage, if you deviate further from the set point, the second stage comes on. So that part's not 2-speed. It's the scroll compressor that's unloaded to have sort of 2 volume flow rates. But the pumping is variable, completely variable. Now on the Stockholm building, I'm sorry, I have just forgotten exactly how the internal heat pumps were controlled. I know it's in our report, I just don't remember, so I won't try to guess at it now.
Singhild, do you remember?
I'm afraid not. I have to look in the report.
Yeah, it's okay. Okay, thank you. We go on to the next question here. And there was a question, more a statement, but I'll read it and you can react to it. It's a potential of improvement of system efficiency with need-based individual room control for ventilation, heating and cooling would be an interesting area of investigation. Any comments to that, Jeff?
Sure, I can agree. It would be interesting to investigate that along with just overall how the distribution system might be improved. I don't know if you, depending on your experience with research projects, sometimes you go along investigating, come up with some nice conclusions and realize, this one part would be really interesting to go into further, but it's just, we don't have the, we didn't have the measurements and the time and so on. So, but I look at it and see how, we would really be nice to improve the distribution system and see if at least the controls can be improved.
Yes, and then we have the next question here. It is circulating pump optimization seems to have a great impact on SPF. Implementing of such optimization approach to a case with centralized system could help to improve the SPF 5 ? Or need use distributed one to get similar results. We can read the question here.
I can see it. So yes, I agree. I think the circulating pump optimization could also have a significant impact on central systems. You could see when I showed the bar charts at first drop, that was the source side circulating pump. The interesting thing about that is that it was a variable speed pump, but the minimum flow was set so high that it almost never deviated from the minimum flow. And, you know, I'm quite confident that say minimum setting could have been reduced and it would have saved energy. The owners were reluctant to change it because they thought they needed 8 liters per second just in case, and maybe they did. So, but that was one of the things we called out, and it was never really tested. So.
Yes, then we have a comment from the audience here. I think it's just a comment that is probably 2-step non-speed controls heat pumps in Stockholm as well here.
It seems likely, but I would rather not. I would rather not make a statement on it until I go back and check.
The information is in the report, so we can check. Okay, next question here. Low delta T in distribution really affects performance on heat pump systems. Maybe this could be increased by putting loads in series. Do you have any comments to that?
Sure, possibly that could be done. You know, again, we didn't investigate the distribution side enough to make any to draw any conclusions on this. But yes, low delta T does affect the distribution side. It also affects the source side. One of the reasons we didn't have a performance factor level 0 for the student Hpt was that they used a relatively low accuracy delta T sensor or temperature sensors on the ground heat exchanger side, right? We didn't know at the beginning how important that would be. And because of that, combined with a very low delta T, because the set point for the flow was so high, it was the uncertainty was very high. So that's why there's nothing reported there. But I do agree that looking at the distribution system could be very useful. So.
Yeah. Yes, then we just have a comment here that adequate control systems are obviously necessary. Yes.
Well, I mean, it's hard to disagree with that. I will say that the ASHRAE headquarters building had what I consider to be an adequate control system, and it was commissioned, and it was, but nevertheless, there was this one set point, and I may have made it sound like I was involved in changing the set point. So to be clear, an expert engineer who's since passed away, his name was Kirk Mesher, he was at ASHRAE headquarters one day. He looked at that mechanical closet, which had a little gauge showing the pressure set point, and he said, that's too high. Right, so it had run for 4 years like that. So my view is there's a lot of room for optimization, right? It would be nice and wonderful to get to the point where we don't need a Kirk Mesher to come in and, you know, say, oh, that's too high, right? And so adequate control systems are necessary, but maybe not sufficient to get good or to get optimal performance.
Yes, thank you. I don't see any more questions in the chat. Do we have anyone who wants to raise their hand and ask a question? We could have room for one more question or two.
Carlene, could I answer your question you asked earlier?
Yes.
Singhild, you asked about how to treat the heat losses from the buffer tank.
Yes, yes, yes.
Right. So in the student Hpt building, we have a buffer tank, but we also have this circulation system on the Legionella protection system.
Yeah.
It's more or less, it's fairly close to a constant heat loss year round, right? So if the building air temperature is roughly constant, you know, even if it varies a few degrees C, circulating all the hot water around, it's just like a constant heat loss. So what did we do? What I did is I looked to check to see if heating was dominant, the dominant load. And for those hours where heating was dominant load, I said that was a benefit. Where cooling was dominant, I said it was not. That's an imperfect solution, but it was the best one that I could come up with at the time. So that's how we treated those losses, whether they were beneficial or not, which I think was your question.
Yeah.
Sometimes the buffer tank is great if you need heat. I mean, it doesn't matter so much if you lose a little heat, but this building actually had significant cooling loads. So
yeah, if you have a heating demand and the storage tank is placed there, you shouldn't calculate all the heat as lost, but on the other way, if you have a cooling need, it's definitely a loss, because then you pay for it twice, exactly. Yeah, so so that's thank you for that answer. I can't see any raised hands here, so I think we go on and let Singhil Gelin in to make the final presentation here.
Thank you, Caroline. And thanks to all the other presenters, which have now given you a kind of sample or some examples of the kind of projects and measurement programs that we have dealt with within the annex. I'll see if I can share my screen. There, you see it?
Yes.
Good. So what I'll do now is just to round up this webinar to show you a summary of the deliverables and reports and outcomes general from this annex, so that you can look at it yourself afterwards. It's all available on the website. Before you throw yourself to our website and download all the reports, I want to say that not all of them are available right now. Some of them are delayed due to some other publications that need to be available first, to be published first elsewhere. So there will be all the reports that are listed on the webpage documentation will be linked eventually, but some of them are not available at the moment, but they will be. Right, so to sum up what we've done within Annex 52, within subtask 1, we wrote up an annotated bibliography of previously published long-term performance monitoring of larger ground source heat pump systems for commercial, institutional, and multifamily buildings. And they contain 82 publications that describe ground source heat pump systems in 17 countries. So the annotated bibliography shows details of, it's like very short summaries or overviews of each publication, who's written it and so on, and also what it contains. We also have 32 ground source heat pump case studies projects in 17 countries that were monitored, and 29 are completed, and we'll have individual reports, but not all of them are available at the moment. Most of them are, I think 25 or something like that, last time I saw. There is also a 2-pager case study summary report that summarizes the similar data from each of the 29 monitoring projects. So you can take a look at that. That's not available yet, but it will be published shortly. Within subtask 2, we published this instrumentation guideline, and that was that was our main purpose with subtask 2. But along the way, as you noticed from the previous presentations, the uncertainty of the performance factors became an issue. We realized that was an important part, and that not so many people did that. So that's why we decided to publish an uncertainty guideline, calculation guidelines, to help more of these calculations being done. So that was sort of the subtask 2.5. Then we have a subtask 3, within which we developed this extended system boundary schema, and we also identified target groups and the corresponding questions that they may have in terms of why long-term performance monitoring projects are important. And then we also published this key performance indicator guideline, what kind of key performance indicators we need, how they are defined, and which are suitable to use for larger ground source heat pump systems. And just to show you a little more in detail what they contain, the bibliography, as I said, 82 publications, describing long-term performance of larger ground source heat pump systems in 17 countries. What we could conclude from that work is that the nomenclature for performance indicator is inconsistent and often unclearly stated, or not stated at all. There is a lack of consensus how to evaluate, express and present performance for these systems, and that the existing performance data is too limited to be useful in setting performance expectations. Also, that uncertainty analysis of performance indicators are so far extremely rare, and we hope to change that with the material from Annex 52. The Instrumentation Guideline, it gives an overview of instrumentation that is typically required to measure long-term performance of ground source heat pump systems, mainly larger ground source heat pump systems. And it has a focus on instrumentation, but not on the methods of the analysis. So that for that you have to look elsewhere, but it's on the instrumentation itself. It provides information on heat meters and distributed temperature sensing in ground source heat pump studies. It addresses measurement intervals and data storage issues, discusses challenges of data management and some methods to address these challenges. And an important thing is that the guideline, though we have written it up with a focus on large ground source heat pump systems, most of it is directly applicable also to air source heat pump systems and air conditioning systems. So even if you're not if you're not yet a ground source heat pump fan, you can have use for it, and anyways, as long as you're in the heat pump system and air conditioning system business. Then for the uncertainty calculation guideline, as we mentioned, it's an important tool to help understanding the significance and result, not only for the ground source heat pump systems, but for any measurement program. So it gives an overview of the uncertainty analysis and the definitions in these analyses. It discusses sensor errors and typical specification formats for sensor uncertainty, and it covers various parts of the measurements and calculations. The focus is on calculating performance factors over a longer period of time, but the theory is the same for shorter time intervals, so it could be used also for that. And also this guideline is applicable to air source heat pump systems and air conditioning systems, and actually for other systems too, other measurement programs. Then the key performance indicator guideline, it identifies and addresses different target groups for performance monitoring. It introduces the Annex 52 system boundary schema and explains it. Also relates it to the SEPAMO schema and points out the differences and similarities. It defines and explains recommended key performance indicators for different system boundaries, and also for different ground source types. Like for instance, there are ground water types systems and borehole systems, and some of the performance indicators cannot be used for both groundwater and borehole. So there are other indicators, for instance, for aquifer, for groundwater systems, where there could be clogging of wells and that sort of performance indicators. In the guideline, there is also a chapter with examples of different key performance indicators, how they are used in the Annex 52 measurement project. So there are, I think, 4 or 5 examples from the measurement projects where we show how this particular indicator helped solving this or revealing this, and so on. Another thing I want to point out is that financial indicators are not within the scope of this. So we have only direct performance indicators, not financial indicators. But several of the key performance indicators that we have defined and identified, they provide the material that you need for these financial indicators and financial evaluation. So it could be used that way. Then we have 3 summarizing publications. One is the final report, which is a 29-page umbrella report, which sort of gives you, yeah, just an overview of the whole annex in short. Then we have this case study summary report with a 2-page summaries of each case study. And then if you're really, really busy, but still want to get a good knowledge of what we've been doing for 4 years in Annex 52, we have the 2-page summary with a nice layout. So you can just get the key things, right? And then we have 27 individual case study reports from 29 buildings in 7 countries. That's on the webpage. So to sum it up, Annex 52 has produced 3 guideline documents, 3 task reports, 1 2-page summary, 27 case study reports from 29 buildings. More than this in total includes more than 1,000 pages. It is 119 measurement years that are covered by this, by the annex, by the measurement projects. And we also have 3 sets of open access measurement data series from 2 buildings in the UK and in Sweden. In addition to these Annex 52 specific reports or material or deliveries, we also have 7 journal papers and at least 1 more in progress, 11 published conference papers, plus 2 that are accepted but not yet published and will be published in October. And then 2 more in progress that will be published in December and in May next year, hopefully. Also 16 magazine articles and 10 other related reports and publications related to the measurement projects. And everything can be found at the web page with a link there at the Annex 52 webpage. The reports are directly linked. The journal papers that have open access are linked, but some of the publications that do not have direct links, they are just referenced. But you can find them other ways. So, and here is another. I'll just wrap up with this nice picture of the people attending the first meeting in Malmö in the spring of 2018, and the happy people, happier but more tired people that attended the final meeting in Nynäshamn, my hometown in Sweden, nearby Stockholm, in November 2021. All these people have worked so hard, and they have shared so much knowledge and so much effort. I'm really indebted to them, and I think it's been absolutely fantastic to run this project together with them. I'm greatly thankful, and that sums up my presentation.
Thank you very much, Signhild, for your excellent presentation. Now we have some time for questions and discussion, and I look in the chat here, and I don't think I see any questions, but some good comments though, and that is that we have got the comments are that we have already applied this new guideline to design other mine water heating field research facilities, which was very useful. So it's a good acknowledgement to Signhild here.
Thank you very much.
The
That's
team,
excellent.
yeah, and link to that. And then I also have a comment here that that Annex 52 reports have been referenced in the new UK heat pump guidance document. So that is also, the documents
Excellent.
are used right away. Really nice to hear. And then we have a question here in the end here, and that is, could Professor Jeffrey comment, if possible, on the impact of using thermally enhanced materials like collectors and grouts on the technology economics of the borehole thermal energy systems, energy storage systems? Please, Jeff, could you comment on that?
Yes. Yeah, I'm trying to think of where to start. It's a big question. So the interesting thing about thermally enhanced materials and thermally enhanced materials and then different collector or ground heat exchanger designs is that there's a lot of things that can be done that will improve the thermal performance of the ground heat exchanger. And they really, in a sense, they really truly work. They lower the borehole thermal resistance. You could have less drilling, but in order for them to be economic, so they're technically feasible, but in order to be economically feasible, they have to be rapidly installable, right? So if there are some designs for ground heat exchangers that might take hours and hours and hours or days and days and days of extra labor time, right? And it's hard to recoup that. So in order to be feasible, it's one, got to be installable in a reasonable amount of time. And two, the extra cost has to be, for what like a thermally enhanced material, it has to be recoverable. So there was actually in North America, there was a Canadian company producing thermally enhanced pipe. They've dropped it after several years on the market, they've dropped it. And well, I guess maybe they could answer better the exact reasons, but my reading of the situation was the extra cost of the pipe in most cases couldn't be justified. Now, that may not be completely correct, but that's my interpretation of the situation, right? Is that if it's economically feasible, if it's going to cost, somehow it's going to lower the first cost of the system, or the difference in first cost is going to be met by an improvement in performance. So that's my comments. Yes, I've commented.
Yes. Any more? Yeah, I have something more here. No, it was just. Yes, we have a question here. In principle, long-term monitoring of large-scale ground source heat pump systems could help identify unsustainable operation related to unbalanced heating and cooling load, for instance. Was this an issue in some of the 30 projects of this annex?
Yes, in some of them. Yeah. So I can't point out exactly which ones, but there are some that had a balance problem, and some could adjust it over time. There are examples from Germany. Maybe Franziska, would you like to comment on that? I think Franziska is with us in the audience.
Yes, hi. Yes, we have a big problem with the AOV. There we have the problem with the balance between cooling and heating. So we have too much cooling in summertime, but then we changed it as we put out the IT cooling. So we do not cool down the server since 3 years, and now we have a good balance between heating and cooling. Yes, I think that's the most problem with one of the buildings.
Yeah. Okay.
Olle,
Yeah.
would you comment on that for the Emmaboda system? I think Olle is in the audience. Olof Andersson.
Yes, I'm here. In Emmaboda, that's an industrial application, and it's not. It's very unique in the sense of using geothermal energy and storage. We are looking at very high temperatures at storage, and that is waste heat from industrial processes. And what's happening is that we try to store as much heat as possible during summer to use that in winter for heating the industrial buildings. And we are also trying to keep that in balance. But of course, since you're storing quite a high temperature of heat, around 50-55 degrees C, you will also lose energy from the storage. So we have to compensate for that. And that is around that we can expect to be around 20% of losses that we have. But it has not been run with heat pumps. The system has not been run with heat pumps more than 3 or maybe 4 years by now. And we are not still coping with balancing this fully, at least. Yeah.
Yeah. So the Emma Bodaxylhem high temperature BTES project is very interesting, since it was a pure high temperature storage without a heat pump for the first 5, 6, 7 years, something.
7 years, yes.
And then heat pumps were installed to lower the temperature but improve the overall system performance and system balance.
Yeah, that's right. Yeah.
Okay, thank you. I have a question here. It's coming in more and more questions here. What's long-term measured ground response temperature compared to model response? I don't know, Signe, if you can answer that question.
Long-term measured ground response temperature compared to model. Yes, in some cases it was, but not in all, I think.
Is it
the KTH projects have that? That would be the what would that forskningen and what's the other? Frescati, I think. Willem, are you there?
Hi, yes, I'm here.
You can comment on it.
Yeah, we didn't have it for forskningen, I think, the comparison between model response. But for Frescati, I'm pretty sure there is. So I don't know if Alberto is here. And if you can comment on that.
I don't think so. Yeah, I don't think he is.
Okay.
I also think that the system, the Aalto University system, also had a comparison. At least they have a paper on it. But I'm not sure if it's in their project report.
Okay.
There's also a paper about the comparison in Frescati that I'm sure people can find online.
Yes. Then I have a more general question here. Any general recommendations for future work in ground source heat pumps? If you have the chance to do it again, what are the things that you could modify or change?
Oh, that's a big question.
A big question, yes.
If we would start over with the Annex 52 work, well, of course, we would by now have the system boundary schema, so that would give us a very good push. But yeah, we learned a lot about the instrumentation and what to expect from it. Also, I think it would have been easier to, knowing what we know now about uncertainties, to perhaps change some of the instrumentation programs so that and the measurement sensors and so on, so that we could analyze the uncertainty better and have the instrumentation in the right places earlier, and easier to handle the frequency, the measurement frequency. Maybe Jeff or Claes would like to comment on that. No?
Okay. Yeah, I think in general, better planning of the instrumentation would have helped a lot. So I know on the ASHRAE headquarters building, there was enormous number of research hours spent on making up for lack of having the right instrumentation. Likewise on student Husat they had excellent instrumentation on many parts, but just a few more sensors that were say higher resolution would have helped a lot so that would have helped on the measurement program. And then in addition, we needed sensors on the distribution system, which we didn't have, to really analyze that part of the system. So all those are things that could be done differently for the measurement program, right? And I think we can do it more accurately and more, well, in some cases less expensively, but certainly less expensively in the long run. On the ground source heat pump systems themselves, there's a lot of things, but I think the biggest thing that we saw is there are a lot of part load effects that could partially be overcome with either buffer tanks or possibly different thermostatic controls. And I would say that for practical application, that's a real sort of avenue for future investigation. So that would be my thoughts on it.
Yeah. If I should make a comment on, I think that, I mean, my experience from measurement is that the key is to really do it right from the beginning. I mean, we see so many measurements where you start to figure out after half a year or a year what you're measuring and what is wrong. So my advice would be to be extremely careful at the commissioning of the site. And then secondly, fix obvious problems. We find that almost all systems have obvious control problems. And I object a little bit to people saying that we should put buffer tanks as a rule to fix the problems with short cycling and short operating times. I mean, we are working with very heavy systems. So most of the control systems are not correctly adjusted for, I mean, utilizing the inertia of the systems. So before entering buffer tanks, I mean, why not try to use the weight accumulation capacity of the heating cooling systems and the buildings, because of nothing happens in the building if you turn off your heat pump or chiller for 20 minutes. So, and this is hardly ever done. So we see a lot of systems that are breaking compressors and having extremely poor efficiency due to improper commissioning. And of course, if you measure on these systems that are short cycling, it's kind of a meaningless exercise because there's nothing is working as it should. And very often the systems start hunting each other because there are many controls out in the building. So if the capacity control of the heat pump chiller is modulating all the time, then you get everything to wobble around. So I think get it right from the beginning. And that is the key, both when it comes to the measurement and operation. Then it's much easier to monitor the system afterwards.
Yes, okay, thank you very much. Yes, the commissioning is the key.
Yeah,
To make
add
sure.
something there.
Olof?
Yeah, thank you. I agree with Claes that you have to be very careful in the start of any project. It's already in the design stage. I think you have to consider to have a right size of a heat pump. To my understanding from the results from Annex 52, there were too many systems that has too big heat pump capacity to run in an effective way. And that's a very first step, I should say. And then in the design stage, you should also think of making the system as flexible as possible to be able to change the system in accordance to the actual demands of a house, of a building. And these buildings, they may change in their demands due to that it comes in other occupants or whatever. So that's a second step I think you have to think about. And of course, like everybody else said, that you also like to have a instrumentation that allows to trace failures or mistakes that you are doing and or what you find during operation. That was, I think, the most important things that I come to think about.
May I make a remark on that?
Absolutely.
Yeah, I mean, I think that, I mean, this is a standard response in almost all sites we see, is that the heat pump or chiller is oversized, and still it is capable of running, you know, down to 20% or whatever. And if you take most domestic heat pumps, they are on off 100% and almost 100. I mean, taking 100% of the capacity, they still are with very simple control measures. They operate for 15-20 minutes at minimum, using the accumulation of the radiator system and the building to do that. So I basically disagree with saying that you cannot control these commercial heat pump chillers in a much better way than they are done. So I think it's much more. I mean, I don't want oversized heat pumps, obviously, but I think that it's, to a large extent, it's easy to make them operate well if you adjust the controls. But as people say that it's a question of design, nobody is dealing with adjusting the controls, and it's between the capacity control of the chiller heat pump and the building. So they blame each other and nobody's responsible. So I think that almost all the cases we see, you can fix them without buffer tanks or without installing different heat pumps. So don't give up. I mean, you can do much more than what is normally done to get them to work well. I mean, I don't advocate too big. I think that you should have a well designed for part load, because that's what you are working with most. So I don't disagree with correct size of heat pumps, but don't just accept that it's an oversized heat pump. And try to make it better with the controls, but you have a lot of accumulation and buffering in the buildings.
Yes, thank you. I saw a question in the chat by Willem, and maybe you can pose a question yourself instead of me. I saw you were there. You had a question in the chat. Yes.
Yeah, I mean, it was more of a general question of what is what's going to be the continuation of Annex 52. So what are the next steps, basically? And then I'm especially interested in how to use data, perhaps in some automatized way to improve the performance of systems. So I guess, I don't know, Signil, I guess you're the best person to answer.
Yeah, so first of all, what we hope, of course, is that the guidelines will be used and the method, the system boundary schema will be used, and the terminology will be consistent in the future. So that's the first step. The next step that we were hoping for as a continuation of Annex 52 is that to use the results from Annex 52 for another international collaboration program or project that would look into system control optimization, and automatic fault detection. That would be a much more industrial oriented project that would necessarily involve other types of researchers and different industries that were involved in the Annex 52 work. But as I see it, to do that annex, which I really hope will happen, the results from Annex 52 were necessary to investigate or to the results are necessary to take this second step. But I'm not going to lead that project. It's going to be some other project group, and some of the researchers and industry partners that have been involved in Annex 52 would probably be very interested in taking part in that project as well.
Yeah, but there is a need at least to go on with that, I think. Yeah.
Yeah, definitely. Yeah.
And if you have
Thanks.
anyone in the audience here who would have an interest in leading such an annex and creating it and setting up, so please contact us at Heat Pump Center. Contact me, and I will guidance you through the processes within HPT TCP. I think it's an excellent proposal you have signaled.
Yeah, another comment that I'm thinking of for the maybe not the next step, but a side step or a further step in general on research is that what I did not expect from Annex 52 when we set out with the work was that so much of the results of the conclusions would be about things that weren't really not necessarily related to the ground source part or even the heat pump part. So as you could see, most of the performance, the overall building performance, building performance actually happens on the distribution side. We've been pressing on that for several of the presentations, but so I think a very important part of Annex 52 is to point out that this is a more general issue that should be approached on a wider or with a broader perspective than just heat pumps or ground source heat pumps. It should be a building operation, building physics level. So I mean, if we learn from our experience from Annex 52, from the measurement
Now we lost signal, didn't we? Sorry, signal. You froze.
I think so.
You froze. It worked really well today for the whole day, but you froze. Okay. I will write her a message that she disconnect and connect again. But I can see here we have had some other. Now it's difficult for me to see when I stopped. Yes.
It's there.
Signaled. No, she disappeared. Yes. Okay. We have some questions here about short cycling. Sorry, now it moved around for me here. Short cycling or performance could also be linked to poor water quality, corrosion, and bacterial growth. Is there any monitoring of the fluid quality into these studies or any recommendations for future projects? Is it anyone online? I don't know if you have signal here that could answer. Jeff, maybe could you give an answer to that question?
Yeah, I don't remember any places where water quality was an important issue, but obviously, if you had an open loop ground source heat pump system or aquifer thermal energy storage system, that's really where it comes into the water quality seems to be the biggest issue. So.
If I may,
But I don't remember anything specific from our projects, but maybe Signal does.
But yeah, Jeff, if you have poor water problems, I mean, you get the worst heat transfer. So it's basically reduces your capacity. So it would basically work the other way around from short cycling. I mean, unless you are so bad, so you get that the system trips.
Right.
But it's yeah. So I wouldn't see it as resulting in short cycling. It would result in a poor performance and then possibly that the system trips.
Yeah, I will say the key performance indicators have some performance indicators related to clogging or deposition on heat exchangers, but I just don't remember any case studies it actually coming up. So,
Jeff, can you hear me? Sorry,
Yes.
it's Dave.
Yeah.
I remember there were a couple. I don't know if Henk's on the call. I think there were a couple of examples that may not have made it into the case studies where there were stories of clogging in the Netherlands.
Yeah.
And I'm really interested in it, and it's something that people ask about. And in one of the small open loop schemes in Cardiff, I think we can say the injection well capacity or the water levels on the injection well didn't change over 5 years. So from that, we took it that it wasn't clogging. But what we'd have liked to have done is done more like repeat surveys, downhole surveys, to have a look at that well screen and see how it was faring, because there was some iron precipitation happening in this aquifer. So we are doing some ongoing monitoring of the groundwater chemistry and stuff. But I think, so all we could say is, well, within the first 5 years, it didn't cause a problem. But could these be emerging issues? So I think it's an area of interesting, and the biogeochemistry side of things, microbiology, and I think it's a future area of research for sure. Very interdisciplinary.
We just had in France a kind of research that showed that heating pump, air source heating pump, could be affected up to 23% in its performance by poor water quality. So I guess a water source heat pump could be affected the same way regarding the system, but maybe some future improvement for future projects.
Yes.
I'll raise my hand.
Yes. Welcome.
This way. Now, I understand you are talking about groundwater source heat pumps or aquifer storage. And that's something very different. You always have to consider what the chemistry as a main factor or as a key, what do you call it, the key indicator. And you have to expect that you're going to have problems with either corrosion or incrustation of iron or manganese and things like that. So, and that is called clogging. And clogging is a very, very common subject when it comes to these kind of systems. When it's closed loop systems, I haven't heard of any such things.
Okay, thank you. When checking the chat, I can't see any more questions. I see a lot of comments that heat pumps and distribution systems should be designed together, and we could use AI for that, and so on. So you can all see the chat here. Do we have any more questions or comments to Signhild or any of the others that have presented today?
Caroline, I see there's a comment that the buffer tank is a big entropy consumer. You need to have stratified tank for that matter.
Yeah.
Yeah, of course, it would be interesting to compare the entropy generation of when the heat pump is short cycling, or the entropy generation of the control valve being actuated, et cetera, and comparing it, which I think is really the issue there. So yes, of course, the better insulated the buffer tank and stratification and so on do help.
Yes, of course. Any more of the comments that you presenters want to comment here in the chat? Combining this data with the near zero energy buildings is essential, is another comment here. Yes, we've also got questions about recordings and the slides. Yes, they will be presented. They will be published on the website, and you who registered for this meeting will get a message when we have published them. It will take some days maybe, but they will be published. Any other question or comment to any of the presenters here? You are also welcome to raise your hand or put on your camera. No, I can't see anything. Then I think we have come to an end with this webinar. As you have heard, there is a lot of information and reports on case studies published on the website, openly available for all. And I would like to thank all the presenters, and especially Signhild, who has led this annex and organized this webinar with good support from Jeff, I believe. So thank you very much for that, and thank you for listening in today, for attending, and for the constructive questions and discussions. So any final words from you, Signhild, before we end here?
Well, that would be thanks for attending, and please go out there and use the guidelines. Let's improve not only ground source heat pump systems, but also all heating and cooling systems for buildings.
Yes, yes. Couldn't agree more.
And thank you, Caroline, for a good job.
Thank you. Okay, but then we stop for today, a couple of minutes before 5 o'clock. I think it's excellent. So yeah, goodbye and thank you all.
Thank you.
Thank
Goodbye.
you.